And go ahead.
Okay, thank you, John. Okay, so thank you so much for this opportunity. My name is Adan Gomez. I'm from the Computer Science Department. So I'm gonna present this research in progress that I am conducting in our department, specifically in the Cognitive Science program. is is the building a new methodology how to use AI into classroom. So I have called this methodology BBCR. Is called Build, Break, Compare, and Reflect. It's a methodology how to use AI and in order to leverage the AI failures, in order to our students can use that AI failures to understand the human cognition. So it's a research in progress. So I'm gonna share with you my findings so far. So the first thing is, okay, this is a question that started. My research is um, when we ask students to build AI models, write them deliberately, and then reflect on what those failures reveal about the human mind, do they actually come away thinking more like scientists? Because uh, my goal here is not only to understand how AI works, but also to develop scientific thinking skills in our students. So what is the context? Is an undergraduate course at SUNY Oswego where students use free AI tools to model language and cognition. So the first thing is no coding required. So we use no code AI tools. The second, um, uh, the sample of this, the population of this research is undergraduates from the cognitive science program, linguistic, information science, and computer science programs, working side by side in the same course with different theoretical lenses. So Uh, the course is called Computer Models of Language, and we use an active learning methodology with AI tools. And we use this because, AI tools is growing fast in universities, specifically here in America. But almost no one has started what students actually perceive and experience inside these frameworks. So the thing is, my students create AI models using no code AI tools in order to understand how these AI models works, specifically AI failures, and with these failures understand how human cognition works. Okay, so uh, the course, as I told you earlier, is called Computer Models of Language. And what this course is a 14-week course that sits in the crossroads of cognitive science, linguistics, and artificial intelligence. So the students explore how humans understand and produce language by building computational models that are designed on purpose to get this wrong. So the course runs in a hybrid mode using Brightspace. All lab tools are free and require no prior coding experience. So we use uh, tools like linear.ai. We use um, the notebook of Google Notebook, in order that our students can use some libraries and other kind of tools. So uh, other tools that we use is Hugging Face How to Train, Google Colab, and Learner.ai. The disciplines that specifically we work with that is cognitive science and computer science. The methodology, the format is hybrid, in person and online, and no coding required. Students engage with AI models through graphical, no code interfaces. Okay, so this framework is called Build, Break, Compare, and Reflect. So for build a model, so the first phase, our students train their own text classifier or language model using their own data. Every choice they make, what to include, what to label, encodes a hypothesis about how language works. So the first thing is the students create a hypothesis. In that hypothesis, that phase, the students create a model, okay, using an AI, no-code AI tool. Then the second phase is called break. So the students deliberately design inputs that expose the model's weaknesses, not the model's uh, successes or how the model success in a specific field. No, the model's weaknesses. The goal is not to fix the failure. It is to understand what the failure reveals. That is the most unusual part of the framework. So, what a specific scientific skill our student develop in this stage? Systematic observation. So, in the first phase, the students develop hypothesis formation. And the second one is systematic observation. And the third phase, the students look at the patterns in their model errors and connect them to what cognitive science says about how humans process language. The model becomes a mirror, not just a tool. So the students, the same tests that the students run with the model, they apply that test in humans and compare the findings that the students get from humans, compare that with the findings that the students get from the model. Okay, so what is the scientific skill that the students um, develop in this stage is called evidence-based inference, and then reflect. So the students write a structured reflection, what they built, what broke, and what they learn. The focus is on their own reasoning processes, not just the result they reach. So what is the skill that the students develop in this stage is called metacognitive reflection. So this is the fourth phases of this framework. And then what is this study asking? How do undergraduate students in cognitive science, linguistic, information science, and computer science perceive the BBCR methodology? And those working through it help them think more like scientists. So the thing is develop scientific thinking. We want to understand whether students feel they developed specific scientific skills, forming hypotheses, gathering evidence systematically, drawing careful conclusions, and reflecting on their own reasoning. The second one is to discover what is the role of AI failures. We are especially interested in how students experience the break phase, where failure is the point. Thus, deliberately making a model fail change how students think about learning and discovery. And third, the cognitive science and computer science students bring very different backgrounds to this course because we have several majors in the same course. Their different perspectives enrich the discussion, okay? So we want to know whether those differences shape how they engage with and benefit from the BBCR cycle. So this is the 5 dimensions of scientific thinking that we evaluate in this research. The first is hypothesis formation and testing. The second one is systematic observation and data collection. The third is evidence-based inference. The fourth is tolerance for ambiguity and productive failure. And fifth is metacognition, metacognitive reflection. So every single dimension has questions that we use to evaluate those skills. And for that, we apply some instruments in order to evaluate that dimensions. I applied those instruments during the course. So this is the design of the study. So uh, I have applied a retrospective design because the study began after the course was already underway. All data is collected at the end of the semester, was collected at the end of the semester, was 2 weeks ago. So rather than measuring students before and after, we asked them to look back. Students complete the survey twice on the same form, was rating themselves, and they were at the start of the course, and once rating themselves as they are now. Research shows this retrospective approach is often more accurate than true pre-post design because the students now understand what scientific skill actually means in this context. So this is the instruments that I have applied to our students. The first one is the STSS-RPPT survey. It's a 3-5 items Likert survey, 5 dimensions, then and now rating side by side. So it's submitted as a text file. The second one is a BBCR SALT survey. It's how learning gains survey adapted for the BBCR context, how much each course element and activity contributed to growth. Uh, Also, I have conducted individual interviews to the students, one 45-minute conversations with selected students. 6 phases was a semi-structured interview. And as well, I have created focus groups with the students, group discussions of 6 to 8 students stratified by major, 75 minutes facilitated. And the students have written reflective journals as well. So written reflection for the reflect phase of each lab. We have conducted 4 labs during the course, and I got those reflective journals from the students. It was a real-time qualitative record of learning across the semester. So this is the every single survey that I have applied, the STSS RPPT and the BBCR SALT. What is the structure? This is the structure of every single survey. And this is the qualitative side of the study. So this is the structure of the interviews and the focus group discussions. Right now, I am in the analysis data analysis phase of the research. I am analyzing right now during the summer every single response of the students from the surveys and the interviews right now. And how we will make sense of the data. So first, for the quantitative part, I'm going to apply the pair t-test. I'm going to compare each student's then and now scores to see how much they shift on each dimension. I'm going to apply effect size. In other words, the coherence measure how large those shifts actually are. Statistically significant does not always mean meaningful. I'm going to apply Cronbach's alpha as well. Check that the items within each dimension are generally measuring the same thing. I'm going to apply the Pearson correlations, explore connections between dimensions. For example, does a high score on the break phase relate to the high score on reflect? And I'm going to create some group comparisons, examine whether cognitive science and computer science students show different patterns of gain. And for the qualitative part of the research, I have called that part the stories. So I'm gonna conduct a thematic analysis, identify recurring themes across journal entries, interview transcripts, and focus group recordings. I'm gonna apply inductive plus deductive coding. Start with what emerges from the data, then check it against the BBCR theoretical framework. I'm going to apply intercoder reliability. A second researcher codes 20% of the data independently to confirm the themes are grounded, are not just interpretive. And two points more, two more qualitative points called joint display and relative journals at longitudinal data. So what we expect to find, what is our first prediction is we expect the students to report the reflect phase as the most valuable for scientific thinking, consistent with research on metacognition and self-regulated learning. Students often do not appreciate how much they have learned until they are asked to describe it. The second prediction is break is underestimated at first. So we expect many students to initially feel more frustrated than curious during the break phase, but not recognize its value in hindsight, whether the retrospective appreciation show up clearly in the data is one that studies central questions. The third prediction is computer science students will likely more comfortable in the build phase because in this phase they they build a model, and the cognitive science students will likely feel more at home in the compare and reflect phases. We expect those differences to narrow by the end of the semester. So the fourth prediction is students who begin the course with lower tolerance for open-ended problems. Those we prefer clear right answers. We likely show the largest gains in the TAPF dimension because BBCR specifically trains that disposition through repeated exposure. So uh, where we are right now, okay, right now we have developed the BBCR framework, create the STSS instrument, adapted the SALG instrument for the BBCR framework, build digital survey pages, design interview protocol, design focus group protocol. So I have collected the student data as well. I have conducted the interviews and focus groups, and right now I am in the analysis and write-up phase right now of this research that I have conducted during the spring semester. And okay, what this study offers. First, for educators. So evidence on which phases students find most valuable and which feel frustrating can give instructors concrete guidance for improving future offerings of BBCR style courses at any institution. So I plan to create several um, several versions of this methodology, not only for this course, but also for other courses in our computer science department and for our cognitive science program as well. Second, for researchers, the STSS is a new instrument, it's a validated tool for measuring scientific thinking skills across 5 specific dimensions. Other researchers studying AI integrated or active learning courses can use and adapt it. The third for my field is cognitive science. Almost all research on productive failure is in mathematics and physics. This study extends that framework to cognitive science and language processing, a new and important domain as well, obviously. And the fourth, how to use no-code AI tools in education. So the study's evidence and how no-code tools enable scientific thinking can inform decisions and institutions that want to bring AI educations to students who are not programmers. So thank you so much. I have uh, conducted this study. Not only it's not only me. I am working with 2 students. One from the information science program is called Sarah Ellis, and Avila Lolin from the linguistic department. And in one sentence, this study asks whether asking a student to build AI models that fail on purpose help them develop the habits of mind that define scientific thinking and what their experience of that process actually feels like. Thank you so much. Any questions, comments about this research in progress? And I am all ears.
Looks like a great study and a great design.
Uh, one moment. Could you repeat, please?
I just said it looks like a really nice study and a really nice design. So
Oh, thank you.
it's
Thank you.
work. Any questions from anyone online? I saw a lot of head shaking here in terms of questions. So
question that's not really related to what you presented here. I'm just curious what your background is that leads you to do this sort of empirical research as a cognitive scientist, or what, yeah, how did you get to this point?
Okay, yes. I am using several sources, several theoretical frameworks in order to apply this, specifically from cognitive science and linguistics, because, for example, I have used several authors from active learning pedagogy, pedagogical methodology. Specifically, I don't have the names right now, but I have used specifically for uh, scientific thinking skills. Um, this I have the one moment. Uh, this SALG uh, instrument in order to to know what kind of scientific thinking skills I'm going to develop. So that author that have created this, and the second one, some theoretical framework for mathematics and physics that they because they use failures in order to understand how the model works. So I have applied that methodology in the cognitive science field, specifically for AI models. So sorry, I don't have the names right now, but I can email you that kind of authors that I'm using in this research.
Thank you.
Thank you.
any other questions? Okay, we'll stop the recording. Thank you. This was
Okay.
really good.
Thank you, John. Thank you for having me here.
Well, and thank you for joining us.
Okay, thank you so much.